So we're leading up to our quiz tomorrow. Remember, our quiz will be like every other quiz. We'd like to get something down on paper, see where we're at, identify our mistakes, and learn from those mistakes going forward. Check your gold sheet. This is a short chapter, so I think our chapter 7 test is not next week, but the following Tuesday. And you guys have a short week next week because of parent-teacher conferences, Monday through Thursday. So we're kind of gearing up towards putting all this stuff together on Monday and then wrapping up the chapter. The quiz will include solving systems from 7.1 to 7.3. That's 2 variable systems. That's 3 variable systems. Don't forget about if you get infinitely many solutions, you got to let a variable equal A and solve for an order triple. That's setting up your system and solving it. So the question that Owen asked about with the interest rates from the homework, make sure you could read a problem and write your own equations. And then it's also going to have a graphing inequalities question on it tomorrow. So make sure that you do your homework tonight so you feel well practiced with graphing. Let's just review real quickly. What do you remember about inequalities and or graphing inequalities? So what's special when we're drawing graphs of not equations but inequalities? Okay, if it's a single variable inequality, like x is greater than 3, you may have to choose between an open circle or a closed circle. What if I do an equation that is 2 variables or an inequality that's 2 variables, like y is greater than x? Then there will be lots of points. How do you distinguish between open points and closed points on the graph then? There is going to be some shading. You were thinking about shading. What else do you have to consider besides just shading? When you draw the line, is the line dotted line or solid line? Okay, so however you like to phrase it, write that in your notes. I had somebody last hour who said they think about it like solid or broken. I say solid or dashed. If you say solid or dotted, whatever you say to yourself, write that in your notes. You don't have to write the word dashed. Now, I'm putting line or curve because we know how to graph more than just lines. Back in Algebra 1, when you did linear inequalities, you only did it with lines, probably. You didn't know how to graph lots of other functions. But we could see other functions pop up. Okay. So solid or dashed, how do you decide when it's solid or dashed then? It's kind of like the open or closed, but it's with 2 variables. What determines solid lines? What's that? Oh, less than or equal to or greater than or equal to. It's the or equals to, right? Okay, so make a little note to yourself. Solid is less than or equal to, greater than or equal to. Remember that all the points on the line, all the points on the curve are the points that make the 2 sides equal. So if that is included in the solution or equal to, then that should be solid. If that line or curve is just going to serve as a boundary, but the points on the line don't work because they're equal, not less than or greater than, then you're going to leave it dashed. Okay, so solid is going to have the or equals to. The dashed line is going to just be less than or greater than. Okay, for shading, you may know about some shortcuts, but I am just going to say for right now, for shading, we will use a test point. You can choose any point you want, it just shouldn't be on the line or curve. I like to, if possible, choose 0, 0 because it's really easy to sub zeros in and evaluate. Okay, so if my line or curve doesn't pass through 0, 0, I almost always use 0, 0. If my line or curve passes through 0, 0, and we'll see this in one of our examples, I choose something that's like definitely not close to my line or curve. negative 100, negative 100. And that would tell you whether you shade on that side or not. Okay. So there are two outcomes when you use your test point. You sub it in to the inequality and you see what the inequality says. If the inequality is true, the point is shaded. If the inequality after you test the point comes out to be false, that means that point is not a solution. The point is not shaded. If the point is not shaded, you're going to be shading elsewhere on your graph. So like if we're talking about a line, if that comes out to be false, you're not shading on that side of the line, you're shading on the other side of the line. If we're talking about a parabola and we test a point inside the parabola, if it's true, we shade inside. If it's false, we shade outside the parabola. Okay? So you shade where the point is not. Now, there are some different types of solutions. I don't think you have to necessarily write anything down for the next slide. Just kind of pay attention visually to what we're talking about. So there are different types of solutions you're going to see in systems of inequalities. I'm actually going to go to the middle one first. There's two lines that are being graphed. One is being shaded above in orange, the other shaded below in pink. Is there any overlap for those two shadings? No overlap exists. They're never going to cross each other. So this is an example of no solution. So your solution in a system of inequalities is where the overlap of the shaded region is. Okay, so you're looking for overlaps. Now these other two images have overlap and they've just shaded like where all of the overlap is. So like when they graph this line right here, they shaded to the right. Then they shaded below this line, left of that line and above the last line, and you get this polygon. This is called a bounded region because it forms a polygon or a shape and it's all bounded. It doesn't go on forever. Notice that there are 4 points. On a polygon in geometry, we would call those vertices. So we're going to be focused on our vertices right now. We have 4 vertices that we would like to find in our homework tonight if we see this graph.
What is the second one? No solution.
There's no overlap. The orange is shading above, the pink is shading below, and they're never going to cross. The two lines are parallel. So solution is overlap. And then in this graph, we call this graph unbounded solution because these two lines are moving away from each other as we go towards the left side of our graph. So our solution area just continues to grow. It's unbounded. We don't have a closed shape right there. How many vertices do you have for this solution set? So we're going to label this vertex of 1. So in that problem, that would be nice. You'd only have to label 1 vertex. In the other problem, you'd have to label 4. Now we're going to do an example. We're going to graph the system of inequalities and find the vertices. So we've got negative x plus y squared less than 0. I want to do an example of a y squared because you have one on your homework. And y is greater than or equal to x minus 2. Okay, so first thing I'm going to do is just survey my inequalities and decide solid or dashed. First one is going to be graphed as a dashed line or curve. And the second one is going to be a solid. Okay, so I kind of make that note to myself at the very beginning. Now, the second one looks very familiar to me. What type of shape is that? Y equals x minus 2. That's a line. Y equals mx plus b, right? Okay. So we know how to graph lines in y equals mx plus b form. The slope here is 1 and the y-intercept is 0, negative 2. Okay, so I'm going to go ahead and graph that one first. That's a quick and easy one for me to graph. Okay, so I got 0, negative 2, and my slope is 1, so I would go up 1, right 1. I could repeat that a few times if I wanted to, just for safety there. And I'm going to draw this one as a solid line. Now, at the same time I graph it, I like to decide where to shade. So I'm going to use a test point. This graph, this line, does not go through 0, 0. So I would like to test 0, 0. So I'm going to test 0, 0. And that means I'm going to put 0 in for x and 0 in for y. So is 0 greater than or equal to 0 minus 2? 0 is greater than or equal to negative 2? True, right? That checks out. So that means on my graph, I would want to shade where 0, 0 is. So I'm shading above and to the left. Now, I cannot shade on the smartboard, so I'm just going to use a little arrow here to point in the direction of where my line is shading. If you want to lightly shade, if you want to do gradient shading on your homework and on your quiz and stuff, that's fine with me. I just can't do it. Okay, now we got to graph negative x plus y squared is less than 0. So you haven't really ever seen anything like this before because the y is squared, but what do your graphs look like when x is squared? They look like parabolas. So this is really a parabola as well. The difference is because y is squared, not x, it's a parabola that opens sideways. Okay. So how I'll go about doing this, because we haven't done sideways parabolas yet, is I'm going to take over here, actually I'll extend my screen. I'm going to take negative x plus y squared less than 0. So negative x plus y squared is less than 0, and I'm going to solve for y. So add x, square root, y is less than plus or minus the square root of x. So if you're solving a y squared problem and you solve for y, you'll always have to add that plus or minus, which means you're going to have two square root graphs. One's just a reflection of another. So like, remember your square root graph is that little thing over to the right, the little bump? And then if we have the negative version of that, it's the other little bump. So there's the other arm of the sideways parabola. So if I wanted to graph that, I might just choose like some x's and some y's, but we also know what the square root graph looks like. What would be some good x's to put into this one? 1. What else is easy to take the square root of? 4. What else? Smaller. 0. Now those are the same points in the parent graph of the square root function. So some of you may have been able to graph by parent graph, okay, which is fine. So I'm going to plot 0, 0. I got 1, 1. And I've got 4, 2. And this one's dashed, right? And remember, this is supposed to be a sideways parabola. The other arm of that parabola is the negative version of that graph. So it's always a reflection of itself. If you want to do another table of values, you could. But I know that it's going to reflect at 1, negative 1, and 4, negative 2 down here. All right, so for the parabola, I have two areas where I could be shading a parabola. My shading for the parabola could be inside the U or outside the U, all the way around. In order for me to figure that out, I'm going to use a test point. Now, 0, 0 is not going to work for me this time because my parabola goes through 0, 0, right? So it's going to be equal. It's not going to tell me true or false. So I need to pick a point somewhere else on my corner plate. It can be anywhere. I usually pick points that are obviously not on the graph and obviously in one region or another. So I'm actually going to pick a point that's outside the parabola. I'm just going to choose -3, 0. Can you choose a different point if you want? Yes. Okay. So I'm going to test -3, 0. Which means I'm going to be plugging -3 in for x, so that would be -3 plus y squared, which would be 0 squared, and that's supposed to be less than 0. So I'm plugging that into my original inequality. -3 plus 0 squared is less than or equal to 0, or sorry, is less than 0. That gives me 3 plus 0 is less than 0. 3 is less than 0. How do you feel about this? No good, right? This is false. So when you get a false solution, you look at this 0.30 that I have back behind the parabola. It should not be shaded. That's outside my parabola, so where should all my shading be? Inside my parabola. I can't lightly shade inside my parabola, but you could. It's inside the parabola, and now you focus on where are the two overlapping. I'm above the solid line. I'm inside the parabola. I have a bounded region with a curve. Questions so far in the graphing part? Yeah. Just because you could draw open circles only to mark the places where I was going to draw my dash line. Because that's dashed, that to me means the whole thing is dashed. So if you would prefer to mark them as open circles, that'd be fine. But I would assume if you plot those points to draw the curve, but you draw the curve dashed, then the whole thing is dashed. Good clarifying question. Okay, now before we leave this problem, we gotta focus on one last piece: the vertices. Vertices are places where two curves, lines or curves, are intersecting each other around the shaded region. So here's my shaded region, and I'm looking for points of intersection. I have a point right here, so I'm going to call this V sub 1. And I have a point right here, this is V sub 2. If from your graph you can identify where the vertices are, then you can just label them from your graph, but you should make sure that they are actually true. So if you were going to tell me the coordinates of V sub 1, it looks like it might be where? 4, 2. To check to see if that's true, you could plug x equals 4, y equals 2 into both of the equations, and they should be equal on both sides. They got to be a point on the parabola and a point on the line, and those points are when they're equal to each other. So if you did -4 plus 2 squared, is that equal to 0? Yeah. And if you did 2 equals 4 minus 2, is that true? Yeah, so 4, 2 worked in both equations. That is true. What about V sub 2? -1 is what it looks like, right? 1 to the right and down 1. And so if you want to just double check, -1 plus -1 squared is 0. True. -1 equals 1 minus 2. True. So that's a point on both curves. Okay. So I'm going to put a box around this because this is really important. That's what you want to be doing today. It's going to pay off for you on Monday. Any questions, concerns before I leave this? All right, let's try our next example. And I'm going to give you some hints on this one to make your graphing life just a little bit easier, in case you didn't know that it could be. I'm graphing lines in standard form. This is a nice one to do. It's going to pay off again next week. We're doing linear programming. So we've got x plus 2y is less than or equal to 6, x plus y is less than 5, 3x minus y is greater than or equal to 5. Okay, so my favorite form for the equation of a line is y equals mx plus b. True? I don't know if you feel the same way, but I love slope-intercept form. However, when doing this with lots of equations in standard form, and next week you're probably going to have like scaled graphs, it's harder to do slope-intercept form when you're scaling your graph. So I use a different method for these graphs. If it's in standard form, I use an intercept method. So I'm going to find the x-intercept and the y-intercept for all of those lines, and then I can just connect them with a straight line. So I'm going to make an x-intercept and a y-intercept. Okay, and let me ask you this question. If you want to find an x-intercept in any math class or any function, what do? Plug 0 in for y. So if we put 0 in for y, 2 times 0 is just 0. What's x equal to? 6. And if you want the y-intercept, plug 0 in for x, well, that would just be 0 plus 2y, which is 2y equals 6, so the y-intercept is 3. I also call that my cover-up method, where I just cover up the other variable. So if I want the x-intercept for x plus y, cover up y, x equals 5. Be at 5, 0. And the y-intercept will be at 0, 5. And then in the last one, when I cover up y, I have 3x equals 5, so my x-intercept is at 5/3. I'm okay with that. And then when I cover up x, my y-intercept is where? -5. Yeah, you gotta be careful on that one. That's negative y equals 5, so y equals -5. Okay, anybody confused about how I got my intercepts? Have you seen that before? Some people have? Okay, I love it. It makes it a lot easier to graph, especially when you're doing lots of these problems that have them in standard form. So now I'm going to draw my graphs and think about shading. Okay, I'm going to go like probably 6 on all sides because I have those intercepts. Okay, set up my graph here. Okay, and then I can plot 2 of the intercepts and draw the line. So 6, 0, and 0, 3, make sure you get them on their correct axes. And this graph was solid, so I used a solid line. I can also do my shading. So I'm going to test 0, 0 because it's not passing through the origin. If I put 0 in for x and y, is 0 less than 6? 0 less than 6? True. So then I should be shading down where 0, 0 is. I want to shade towards 0, 0. If you want to lightly shade underneath, you can. Okay, plot my next intercepts, 5, 5. 5, 0, and 0, 5. And this graph is going to be a dotted line. Again, I'm going to test my shading. I'm going to test 0, 0. Is 0 less than 5? Good to go. So I should shade where 0, 0 is. So this one is shading in this direction. Can you tell my overlap is going to be like underneath this solid line and to the left of the dashed line? That's where my overlap is so far. Okay. All right, last one. When you're plotting 5/3 as your x-intercept, you're just going to put it closer to 2 than 1, right? It's in between the two. And then I have my y-intercept at -5. And this one is solid again. Pretend I went through that point, as usual. And decide where to shade. I can use 0, 0 as a test point again on this one. When I put 0 in for x and y, is 0 greater than or equal to 5? No. So instead of shading towards 0, 0, I want to shade away from 0, 0. Because 0, 0 is not a solution. So this one is shading this way. Okay, how are we doing? I know this is not very exciting material, but I just need some kind of like lifelike response from you. Is this okay so far? Does anybody have any questions? Owen's giving me a thumbs up. That's helpful. And zombies. Okay, good. Okay, so can you tell where your full overlap is? Is it bounded or unbounded? It's unbounded. It's this section right here. Okay, so that's an unbounded region. Even though it's unbounded, you should still be able to find any vertices. So when I'm looking for vertices, it looks like I've got the two solid lines, right, that are crossing. So I'm going to call that V sub 1. And then it looks like I have this solid and this dashed one crossing. So I'm going to call that V sub 2. I only have to worry about like the vertices where two of the lines or curves that I graphed intersect. So that's it, right? The other vertex up here isn't part of the shaded region. So I don't need to list that as a vertex. I only want the ones around the shaded part. Okay. So anybody want to take a guess based on their graph what they think V sub 1 or V sub 2 is? Okay, so V sub 1 looks like maybe 2, 2. Oops, I already have a parenthesis right there. Remember that you should really make sure that that is true, right? So you would take 2, 2, and these are the two solid lines. So you would plug it in. 2 plus 2 times 2 is equal to 6. Yeah, 2 plus 4 is equal to 6. 6 minus 2 is equal to 5? No. So that means 2, 2 is not the correct point. It might be really, really close to 2, 2. What I would do at this point is solve a system of equations. So I could call this like, this is row 1, this is row 2, this is row 3. Well, we're solving for row 1 and row 3. I'd probably solve by elimination. Which variable do you guys want to eliminate, x or y? When you solve systems, you're finding points of intersection where the two lines meet. So we're going to find where the two lines meet. Do you want to eliminate x or y? X. Okay, so I'm going to have to multiply row 1 by -3. That's -3 minus 6y. You don't really need the inequality here because we're trying to find the intersection point. So I'm going to say equals -18. And then row 3 is, oops, I forgot my x. 3x minus y equals 5. So that gives me -7y equals -13. Y equals 13/7. Is that really close to 2? Yeah, so it makes sense that we had guessed 2, right? Or at least the y coordinate was 2, because it is actually really close to 2. So now that we have y, how will we get x? Plug it back in, which means we're going to have to work with some kind of fractions, but we'll deal with it. X plus, I'm doing row 1, x plus 2 times 13/7, so I'll move it up here in a second, equals 6. Again, at this point, you're really solving for the intersection of the two lines, so you don't need the inequality part, you need the equals 2 part. So you can work with equations. So this is x plus 26/7 equals 6. I'm going to subtract 26/7. So this is like 6/1. That's going to be 42/7 minus 26/7. What does that give me? 16/7? And 16/7 would have also been close to 2, right? Okay. So that 2 that we set for our vertex, that is not right. I'm going to change that. Now we know it's really 16/7 and 13/7. Which is close to 2. So that's probably the saddest moment, is when you think you found a vertex and you check it and it's not right. So then you got to solve the system, right? That'll happen every now and then. So be ready for it. What do you think the other vertex is? Anybody got a nice graph where it looks like maybe it's at a nice number? B sub 2? Mine looks like maybe 1, 2, 3, 4, 1. So I'm going to check for 1. That's the graph of the dotted line. Is 4 plus 1 equal to 5? Yeah. And then this line right here, which was the first equation, row 1, is 4 plus 2 times 1 equal to 6. Yeah, okay, so that one worked in both equations. So that's actually the vertex. If you weren't sure, you could solve the system for row 1 and row 2. I'm going to try to avoid that if I can. Okay, what questions do you have for me? Okay, the last one is a homework problem. So whatever page you're going to be doing your homework on, we're going to start one homework problem together because it's one of the word problems. There's one other word problem on your homework. I see a lot of smiles out there, people getting really excited. I wouldn't write all of this down. I would just write that this is page 516. Okay, so there's no getting around this whole word problem business in this chapter, and on Monday it's going to be like word problems and everything all together, all at once. Okay. So we just can't avoid it. We got to face it head on. This one maybe sets up a little bit differently than some of the other word problems, so I'm going to kind of walk you through what I'm thinking about. Not every word problem will be set up like this. Like you've already already done some word problems where you set them up on your own just fine. Okay? But this is kind of a case where you have two unknowns and then you have like two other things that are happening. And so I kind of use a table for my work. So you're going to see me set that up. So we've got a furniture company and they're making tables and chairs. And I find out that each table requires 1 hour in the assembly center and 1 1/3 hours in the finishing center. Then I know each chair requires 1 1/2 hours in the assembly and 1 1/2 hours in the finishing. I only have 12 hours in assembly and 15 hours in finishing. I want to find and graph a system of equalities describing all my production levels. What am I producing? Chairs and tables. So those are going to be my unknowns. I'm going to let X equal tables, and I'm going to let Y equal chairs. So just like we've done before, it's a good idea for you to figure out what is unknown to you. The production level of how many chairs and tables I produce is unknown. Okay. Now, those are my two unknowns. So I've got, I'm going to do tables on top just because that's the order it comes in. Tables, and I've got chairs. And then I know something about the assembly and the finishing centers. Tables require 1 hour in assembly and 1 1/3 hour in finishing. Chairs require 1 1/2 in both. And then we're told assembly has only 12 hours, finishing has only 15 hours. And we had defined our variables. We're going to let tables be X. We're going to let chairs be Y. So when you're writing your, what I'll call constraints or your inequalities, you're constrained by the amount of hours your factory has for assembly. So for every table, it's going to be 1 hour. For every chair, I'm going to change it to an improper fraction, 3/2 hours. And then I can't go more than 12. So it has to be less than or equal to 12. The other inequality is going to be all about finishing, right? Because I have a limited number of hours to finish the chairs and tables. So that will be 4/3 X plus 3/2 Y must be less than or equal to 15. So there's only certain numbers of chairs and tables that I can produce that will fit in those hours that I have for assembly or finishing. Now, there's two other constraints because I'm working in the real world. What's the least number of chairs or tables I could produce? 0. So X must be greater than or equal to 0. Y must be greater than or equal to 0. If it doesn't say anything about the least number, then you want to bound it at 0. That means when you graph this on your homework, you can graph only in the first quadrant. So on Monday, we're going to see that in all of our real world problems, we're only graphing in the first quadrant. It's going to be one of your vertices is going to be 0, 0, because you've got to go above those two, above the x-axis, right of the y-axis. And the other two lines are going to look something like this. I don't know what they are. They're going to cross like that, and then you'll have other vertices, so like vertice 2, vertice 3, and vertice 4. Vertices 2 and 4 are going to be intercepts, so if you use the intercept method to graph, you'll already know what those values are. Vertex 3 is going to be the one where maybe you have to solve the system, and it's going to be shaded below in this problem. It wouldn't always, sometimes it could be unbounded. But you should go through and attempt to graph those constraints, or those inequalities we produced. Okay? So you have a homework assignment. It's only like 4 or 5 problems. We've done part of this one. There's one other word problem. The second word problem, I don't think you need to set it up with the table method, but we will see some next week that will use that table method, so you'll be able to practice it. and you'll take a quiz tomorrow.